Hello and welcome back. We will continue looking at section 4.3 and to remind ourselves, in the last video we saw the product rule, quotient rule, and power rule for logarithms. And we looked at splitting apart logarithms, splitting apart multiplication into addition, splitting apart division into subtraction, and splitting apart exponents into multiplication. So we can do this in reverse, and we can actually combine logarithms. So here we have log of 25 plus log of 4. And what we know is that as long as we have the same base, we can combine these logarithms because addition outside of a logarithm is the same thing as multiplication inside. So again, if you were to look at this in reverse, I can split apart multiplication into addition. So I'm just doing this in reverse. I'm taking addition and I'm combining it into multiplication. However, this we can simplify a little bit. This is going to be log of 100, and when I don't have a base here, this is the same thing as log base 10. And we know that 10 to the second power is 100. So this is 2. Again, we're asking 10 to what power is 100, and 10 to the second power is 100. So log of 25 plus log of 4 is in fact 2. If we continue on, we've got log of 7x plus 6 minus log of x. And we know that when we subtract, we're not going to be multiplying, we're going to be dividing. So here, this is just going to be log of 7x plus 6 divided by x. So again, when we're subtracting logarithms, it turns into division within the logarithm itself. And yeah, so we've combined everything into just one single logarithm. However, we do have to be careful because the coefficients of the logarithms must be 1 before we can condense them into one logarithm. So what we'll notice is that here, the coefficient of this logarithm is 1. It's just 1 times this logarithm. This coefficient is going to be -1, but again, we don't have a 2. We don't have anything other than, I suppose I should write plus or minus 1 in front of here. So we can have a -1 or a +1. So let's do a little bit of work when these aren't the same coefficients. So here I have 2 times the natural log of x, and again the natural log is just log base e of x. But in order to combine these two logarithms, they're going to have the coefficient of 1. So I need to get rid of this somehow. And what we'll do is we'll undo the power rule. So 2 times the natural log of x is the same thing as the natural log of x squared. So again, why are these two the same? Because when we have a log of something to a power, I can pull the power out front and write it as, so I can pull it 2 out front and write it as 2 times the natural log of x. But I can go in reverse. 2 times the natural log of x, I can pull that 2 up top and write it up there. So the same thing can happen with this 1/3. So this is going to be plus the natural log of x plus 5 all raised to the 1/3 power. And now I'm adding everything, and I have the coefficient 1 out front. So I can pull it all together and write it as multiplication. So this is going to be the natural log of x squared times x plus 5 to the 1/3 power. And it's a little bit messy, but this works absolutely fine. Natural log of x squared times x plus 5 to the 1/3 power. That's a perfectly valid logarithm. One thing that I personally like is to write anything to the 1/3 power. I'll write this as the 3rd root of x plus 5. So we still have the same thing, I'm just writing it in a slightly different way. I think this maybe looks a little bit nicer, but this is certainly a correct answer, and so is this. And they are the same thing. Let's do another one. So here we've got 2 times the log of x minus 3 minus log of x. Well, again, we have this coefficient out front that's not a 1 or a negative 1. So I've got to get rid of this. So again, I'm just going to pull it up top. So we'll write this as log of x minus 3 squared minus the log of x. And again, now that I'm subtracting, I can write this as 1 log with some division. I turn subtraction into division. This is going to be log of x minus 3 squared over x. And if I wanted to, I could expand this x minus 3 squared, but I don't think I will. So I'm done. That's right here. So let's go through, I think, one more example. And this one I want to be a little bit more careful on. And I want to do the following. We'll pull in all of the exponents first, and then I'll show a nice little trick to make this a little bit easier. So I don't think I have enough space on the end here, so we'll just write it out here. So I have log base b of x, but it's times a fourth. So I'm just going to write this as log base b of x to the 1/4 power. Here I have minus 2 times log base b of 5. I'm going to keep the minus sign there, and I'm going to pull the 2 up. This is going to be log base b of 5 squared. And then, again, minus 10 times log base b of y, so this is going to be minus minus log base b of y to the 10th power. So what I've done is I've pulled in all of the coefficients, but I've left the negative signs out front. And what I'm going to do next may seem a little bit silly, but it will help in the long run. So what we'll notice is that I have a minus sign here and a minus sign here. I'm going to pull those minus signs out and write this as plus. So what have I done? I've just sort of undistributed, reverse distributed the negative sign out of both of these terms. So now I have log base b of x to the 1/4 minus the sum of these guys. Well, if I'm adding logarithms, it's the same thing as multiplying within the inside. So this is going to be subtracting log base b of 5 squared times 10 to the y power. Okay, we're nearly there. And now I have a log minus another log. This is going to be the log base b of x to the 1/4 divided by 5 squared times y to the 10th power. And we're essentially done. Maybe one thing I can do is I can simplify the 5 squared on the bottom. 5 squared is just 25. This is going to be 25 y to the 10th power. And x to the 1/4 power is the same thing as the 4th root of x. So again, these are exactly the same. I would need to simplify, but I just chose to write it in this way. So the trick here, going from this line to this line, pulling out the negative sign out of all of the negative terms is the most helpful, because then we can combine these into one logarithm with a product in the middle. One thing that you'll notice throughout this entire section is that you need to have the same base in order to combine logarithms or in order to pull them apart. You absolutely have to have the same base. So the question is, what if you don't? What if you have two different bases for the logarithms? In that case, there are some steps that we can take to mitigate that. So we can change the base of a logarithm in the following way. Log base b of m is equal to log base a of m divided by log base a of b. And the question is, if I give you, say, log base 3 of 7, what is this a here? What can I use for this a? And the answer is essentially any base that you want. And I should be careful here. The base of a logarithm, the same as a base for an exponent, has to be bigger than 0. So a has to be greater than 0, and we can't have a base of 1. So any positive number that's not 1. So for instance, log base 3 of 7 is the same thing as log base 2 of 7 divided by log base 2 of 3. I can use any number for a that I want. So for instance, if I have log base b of m and I don't like b and m, I can change that to be whatever logarithm I want, including, let's say, log base 10 of 7 and log base 10 of 3. Or log base e of 7 and log base e of 3. And these last couple are quite nice. Most calculators and computers will be able to handle log base 10 and log base e a lot easier than other things. So these are really what we'll use. So let's summarize that in the following. So we can introduce common logarithms and natural logs in the following way. If we want to take log base b of m and our calculator can't handle taking log base b, we can turn this into log base 10. So this is log base 10 of m divided by log base 10 of b. Or maybe we have a button that's for the natural log, so we can turn log base b of m into the natural log of m divided by the natural log of b. So let's do that. So let's use both common logs and natural logs to evaluate log base 7 of 2,506. So maybe we're using a calculator that doesn't have a log base b of x, and we can't use whatever base we want. So what we can do is we can turn this into, let's do common logs first. So this is going to be the log of 2,506 divided by the log of 7. These are things that we can find on a calculator. We can even type these into Google. If we find the top and the bottom, the log of 2,506 is about 3.4. So here I've rounded a little bit. If we take the log of 7, plug this into Google, you'll get 0.845. And again, I've rounded. When we divide these, we'll get about 4.02. This, by the way, I didn't round. I just plugged both of these in and divided their exact values. But again, common logs, we can type into Google. Most scientific and graphing calculators will have a log button as well. So we can do the same thing with natural logs as well. I can take the log base 7 of 2,506, and I can use base e instead. So I can take log base e, which is the natural log, of 2,506, and I can take the log base e of 7, again, just the natural log of 7. I can plug it into Google, just type in ln parentheses 2,506, and we get 7.83 approximately, and for natural log of 7 we get about 1.95, but in both cases we get 4.02 because they're both the same number. They're both the log base 7 of 2,506. So we should get the same number, and luckily we did. So that's just a brief introduction to all the properties of logarithms.